X1G and 7a together. So here we're looking at now, got the 1 over root x function. This one now when it's 3, so cube, this is 1 on now x to the power a third. Look at that shape. Versus x to the power of 1 on fourth root. And again, it follows a very similar pattern. If you compare these two, so when you square rooted it, the truncus loses the negative side. So you just get that right-hand side. When it's the cube root, the only difference is the growth. Those two. And then same thing again. When you've got the truncus, negative goes away because you're square rooting it. Yeah? And a lot of it, you can actually use composite function theory to actually show why that happens as well. But for now, part of 1G 7a, what do you need to do? I don't want you to memorize all this. Because what they're trying to get you to do is to analyze what's happening to the functions. So they'll give you a random power, and your job is to come up with, well, what would happen if this increases or decreases? Which is why on the next page, I've got these blank where you see a pattern. So I'm going to go through Desmos, and I'm going to get you to see how I go through the first one and what kind of analysis I would come to conclude, and then you do the same for the others, and that is pretty much 1G 7a, because it's the power of you being able to analyze what would actually happen. Okay, so let's start off with, I'll start off with, I think, x to the power of n on 3. This one might be a good one to sort of show you the theory. So here we go. I'm going to go x power of 1 and 3. Let's go to Desmos. All right, so x to the power of n on 3. Slider n. So if I had n as 1, so it just becomes x to the power of a third. That's a root function. That's just the inverse of the cube, so it looks like an s. Very cool. Easy to remember. Well, watch what happens when I start increasing it to 2, then 3, then 4, then 5, then 6, then 7, 8, 9, 10, right? So when I go to 2, we get this symmetrical shape. Can someone explain to me what happened? So I had an S shape before, then now it kind of looks like the bird thing that you draw when you're on the beach. Why does it become symmetrical? Just like all the other ones, why is it every time you have a 2, it becomes symmetrical? Like a truncus function becomes symmetrical.
Inside of the cube root, you're squaring x, so x will always be positive.
Very good. When you square a number, whether it's negative or positive, it always becomes positive. So when it was 1, that was fine. When it's to the power of 1/3, no matter what the number is, when you cube root it, if you cube root a negative number, it's still negative. But when you put a 2 there now, that is actually the same thing as you saying, whoops. If you put a 2 there, so this is x to the power of 2/3, isn't that just the same as saying x to the power of a third squared? Because in our index laws, we know that you can times the powers together. So x to the power of a third you knew, you said it was an S shape. But if you square every value that you can think of, every coordinate, doesn't it all just become positive? That's why it becomes both sides become positive. You know what I mean? Okay, that's why you get that symmetrical shape and then they both go up. It looks like a bird. Okay, so this one looks like a bird. Both of them go up. Then, notice what happens. Well, what happens if I have 3 over 3? A straight line. So x to the power of 3 over 3 is actually x to the power of 1, and it's asymmetrical again. It's asymmetrical, so if I go back here, I'll put a 3. It's not an S per se, but it's a really straightened out S. You see, it was curved like this, and I straightened it up on this side. It was curved like this, and I straightened it out this way. So this is where I want you to see now. What happens if I jump the number 4 and I go to 5? What do you think would happen now if I asked you, what does x to the power of 5/3 look like? Have a think for a moment. So we went with an S for 1 over 3. You said 3 on 3, still asymmetrical, but it's flattened out. So now that I'm going to the power of 5, so on the top, it's still, another way of thinking about it, it's still x to the power of a third, all to the power of 5. I'm doing it to the power of 5. The rate of it is really high now. What do you think it'll look like now? You know what I'm going to get you to do? Draw a graph of what you think. Do it in pencil. Just draw what you think it might look, and I'm going to show you, and I'm going to get you to think, what else could you have thought to confirm that theory? Okay? So just draw it roughly. Draw it on your sheet. What do you think x to the power of a third with a 5 on top? So 5 in the numerator, what would it look like? I'll show you. So just draw a rough one. Just have a guess first. Have your own theories. Here we go. Before I show you the graph, I'll show you another thinking. See, instead of 5, what happens if I had x to the power of a third, but to the power of 9? It's always the odd powers, yeah? So it's 1, 3, 5. Now, what if I went to 9? What does x to the power of 9 on 3 look like? It's a? Yeah. But what does an x to the power of 3 look like? A cube. It's an n. So can you see what's happened here? So watch this. I'm going to write both of them down. So x to the power of 1/3 looks like this. Then we said, well, what if I did x to the power of 5/3? Can you see? Because after that flattening, your rate of power that's increased, it's growing too fast compared to the rate that you're decreasing it. Because third rooting makes it smaller. But fifth root to the power of 5 is huge. So you pass that point, it starts to curve this way. And a way to remember that is, well, what if I went up to 9? Well, a cube graph should look like an n. So it went from an s to an n. You see that? And how you can find that out is find that straight line. So that means that I can ask you a question like, if I gave you x to the power of, let's say, 1 on 50, hypothetically. You see, you know that by the time I get to 50 on 50, it's a straight line, right? So if I did x to the power of 60 on 50, I know it's going to look a bit more like an s. See, so if I just hide these ones, and I do the same thing, I say, all right, well, let's see what x to the power of 60 on 50 looks like. Oh, sorry, that's an even number, I forgot. Got to do an odd number, 61. You see how it curves? Passes that straight line, because 50 on 50 is a straight line, so that means 61 on 50 has to be faster than the actual rate, so it must curve. But you see what I'm doing with Desmos? I'm analyzing it and then coming to my own conclusions that even if I did 50, I still know roughly what the graph looks like. I want you to do the same for exercise 1G and 7A. What happens when it's a 2? What happens if it's a 4, then 6, then 8 in the numerator? Then what happens if you flip that around? What if it was a 2, 4, 6, 8 in the denominator? Because the more you play around and interpret that yourself, you internalize that. Whereas I'm doing it to you, you can only memorize as much as I can tell you. But I want you to actually play around. That's what 1G, 7A, the essence of that is. Otherwise, you can do the exercise. They'll give you the most typical ones, but in the exam, they're not giving you typical ones. They're actually trying to get you to do what I just did. Because I'm looking at it and I'm thinking about it in terms of x, linear, quadratics, the cubic, square roots. I'm using all those relations that you learned from year 11 to predict what the graph will look like. And that's what they want you to do. Okay, so that's what 1G, 7A is. You can take that out. How's that feel so far? Yeah, that's the essence. So 1F was inverse functions. 1G, play around with it. So I gave you a template so far. And that's what I want you to play around. Come up with the theory. So I just showed you the odds. I went from 1 on 3 to 3 on 3 to 5 on 3, and then I showed you 9 on 3. I want you to have a look at what happens with the bird. So it's squared to the power 4, to the power 6, and you would then be able to reason, well, why does it become a bird? Because it's squaring, all the negatives become positives. The S shape now becomes more like both of them shoot up, rather than one up, one down. Okay, then what about 1 on 2? What if you started with square root function? Okay, so 1 on 2, 3 on 2, versus 4 on 2, which is a quadratic, and then 5 on 2, 6 on 2. Okay, so what patterns do you notice? Write your own thinking, and so by the time you go back to 1G and 7A, I promise you, it is so much easier to read. Okay, so don't try to memorize it, try to learn to analyze it. Learn to analyze the patterns that you're noticing, even versus odd, because each one has a slight difference to it. Okay, but the first page should give you most of the properties that you need. That very first page should describe all the properties that you should know for 1G, 7A. The rest is me trying to get you to have a deeper understanding. Cool? Are we good with that? Because I'm also mindful of time. There's now 33 minutes. That can be your time and I can come around and help. If you do need a bit more support on 1G7A, let me know. I'll come around, but that's 1G7A. That's what you're taking out of it. Okay? All right. Sweet. Is there power or even? No, we'll talk about that next session. That's good. All right.